Hello everyone, welcome to lecture 10 of this course. In the previous lecture, we discussed how the data structures, pair and list can be encoded in lambda calculus. Today we are going to discuss functional programming language Haskell, and we want to show how the concepts that we have studied in lambda calculus, they carry on to Haskell. For this, we first discuss the difference between functional programming and imperative style of programming, discuss certain features of Haskell, and also see how function abstraction, application, lazy evaluation or functions, currying, lists are implemented in Haskell. So, the programming languages, there are different paradigms of programming languages. So, we can broadly classify it as how to do and what to do. In how to do, we see there are languages like those that follow the imperative style of programming, that is a C language, the Java and Python. What to do, essentially it is declarative, a functional style, it is adopted in Haskell, that is a functional programming language. How to do means the machine will execute the instructions as given in the code. The machine will not do anything else but this. What to do means tell the machine what is to be done. The machine will do it in some manner which the programmer need not bother about. Let us consider this small example. So, our problem is to compute the sum of the squares of the first 5 numbers. So, these are the first 5 numbers and we want to do their sum. That means we can write sigma j is equal to 1 to 5. Now, consider the imperative version, we have written it in Python. The result is a variable, so initialize to 0, and for I is in the range 1 to 6. That means I value of I will be 1 to 5. I will be taking on 1, 2, 3, 4 and 5. And what we are doing is we are updating the value of the result. A result is equal to result plus I square. That means 0 plus 1 square, that will be 1. Then the value will be 1 plus 2 square, that will be 4, and so on. This is how this program is going to do the computation, and ultimately we are going to get the sum of these 5 numbers. So, this way of doing is called how to do. That means we are telling the machine what are the instructions it has to execute, and the machine, if it executes this, we are going to get this result. But let us see whether we can do it in some other way. So, in Haskell we write, so sum squares is our function. It says the type of the function is int. That means the return type is int. That means the sum of the squares value will evaluate to some integer. Now, it is defined in this way, sum of the squares equal to, that means it defined as, it says that here so this is the list, this is what is input, this is the list that is input to this function. First what it does, there is a function, inbuilt function called map. So, map this raised to means every element of this list will be squared. So, from this list L, we are going to get another list L prime. This is our new list. Each element, map means each element of the list will be transformed in some way. Here the some way is square. So, we are getting a new list, that is 1 square, 2 square, 3 square, 4 square, 5 square. Now, there is an inbuilt function sum, that given a list it will return the sum of the elements of the list. Elements are all assuming to be integers. So, this function will do the same thing what our this imperative program has done, but the idea here is different. In mathematics we write it in this way, we write sigma j square, and this definition that we know, that is exactly represented in Haskell. So, we have taken as input our L was a list, we performed j square, and then what we did the sum. So this is called what to do, in contrast to what we have done is how to do. So let us see the key differences between these two styles of programming. One is the how to do, the imperative style, another we call it as the functional style. So the first one is the imperative, we do step by step instructions, and in functional we do expression of relationships. The control flow in functional, in the imperative language, it is by loops. We have a for loop or a while loop. On the other hand, in functional programming language, we do not have any for loop or while loop. It is using function composition. That means we are transforming the input using the functions, and we are getting the desired result. So here we have variables, and the value of the variable changes as the program is executed. That means we call it mutated. Here the variables values are not changed. It is like, it is not the result value is 0, then result value becomes 1 and so on. It is not like that. There are no updates on the values. It is just taking new values. So they are immutable. So that thus then we have imperative programming languages, we can say they are state based. And we know, we have studied the Turing machine, it is state based. That means it moves on from one state to other. And when we say programming language, it means state is a value of all the variables at any point of time. And that changes on as the program gets executed. Here it is not like that. Here there is no assignment in Haskell or functional programming language. So that state concept does not come here. So here we have essentially a term, and the term is transformed, as in lambda calculus like beta reduction, we get a new term, it goes on, and ultimately we get to a normal form, and that is when we stop. So the idea here is, we have the mindset in the imperative languages is how should the computer work. That means in essence we are telling, instructing the Turing machine all the steps that it has to perform for a given task. On the other hand, in functional language, what is the problem mathematically? The mathematical representation of the problem is what we want to feed as input to a Haskell program. Once that is done, this is what we are expected to do in functional programming language. Now every function in Haskell is a mathematical function. By this we mean that for the same input it is going to give the same output with no hidden side effects. It will not do anything else other than what it is supposed to do. We can have side effects in a imperative programming language. For example, I may update a global variable besides what I have done. That is called a side effect. So as in lambda calculus, in functional programming language there will be no hidden side effects. As in lambda calculus, functions in Haskell are first class citizens. By this we mean that we can pass functions as arguments, return them, or build new ones dynamically. So for example, apply twice fx is you are applying the function f 2 times, composition. So this is your, as if the Church numeral 2. So we are applying f 2x once, then the result that we obtained again we are applying f to it. So the first concept that we take is, so for example, we know that conditional flow is implemented in if then else in imperative style of programming, or in normal anything based on imperative style we do if then else. So guards in Haskell are a neat way to make decisions inside function definitions. So they look a little bit like if then else, but it is more elegant. So in Haskell the program is executed in a top down manner. So the line 1 will be executed, this is line 1, then line 2, and this way the Haskell program will be executed. So the first function says it takes input as integer and it returns an integer. If n is input, this one says, so then this structure, this is called a guard. So and these are the, this is written in pipe, it is written this way, that pipe n greater than 0, it is a guard. It is a condition that takes is n is greater than or equal to 0. If that be the case, then body of the function is returning n. Otherwise, that means what? That means this is false. That means if n is less than 0, then the value will be minus n. So we are returning the absolute value of n. Otherwise is not compulsory. We could have written n less than 0 as well. Otherwise means that all the preceding guards are false. That means if there are G1, G2, G3, Gn, this otherwise means G1 is false and G2 is false and all the way to Gn, all of them are false. That means this be the condition, then we are going to execute the right hand side. So you see the correspondence between this and the standard way. So we write if n greater than equal to 0, then n, else minus n, and this is the standard way of writing of if then else, and we have written using guards. We are going to use guards subsequently in our other programs. So for example, let us see the factorial function we have studied. So factorial of n, consider this, it is taking an integer as input and returning another integer. So if n is equal to 0, here equality, testing equality written as double equal to. So the first guard says if n is equal to 0, then we are going to return 1. Second guard is telling if the value of n is greater than 0, we are going to multiply n with factorial of n minus 1. So this will be recursively executed. So there is recursion here. Otherwise means n is not equal to 0, n is not greater than 0. That means the value of n is less than 0. So you are saying otherwise error, negative input not allowed. So this is the same as writing in our conventional manner in like imperative style. If n is 0, then 1, then you can say then return 1. Else if n greater than 0, then return n star factorial n minus 1. Else error, something like that. Now in lambda calculus we have written this factorial in this way, that if we know the if function, so lambda n dot if is 0 n, if is 0 n is doing this job or this job, else is 0 and n is 0, we are going to return 1. So this part we are doing successor of 0. Otherwise we are doing multiply n factorial of predecessor of n. So here we are doing only this part. We are assuming because it is a Church numeral, so the value of n is greater than equal to 0, so we did not bother about this case. So here the Church representation is this, and you can see this is more or less these two things are similar to this one. Now a second example is, we are taking as input a pair of integers and we are returning another integer. First guard says if the first component is greater than the second component, they are returning the difference between them, x minus y. If the second component is greater than the first component, we will return the difference, that is y minus x. If that is not the case, that means it is not x greater than y, that means x is less than equal to y. And it is also not the case that y greater than equal to x, that y less than equal to x. Combining these two, that means if x is equal to y, that means they are same numbers, we are saying this is not allowed. Just some printing things we are doing, error type. Now in Haskell, as we have seen the pairs, we need to extract the first and the second component. So there are inbuilt functions like fst and snd that we have defined for pair. So fstxy will give us x and sndxy will give us y. Next feature about Haskell is a list comprehension. List comprehension idea comes from the set builder notation. So when we write in set, like this notation says that set of all x's such that x satisfies some property px. So for example, if we have this set of numbers 1, 2, 3, 4, 5 and we write this way that if x belongs to x, x greater than 2. So this is the property we are telling. That means if x is belonging to S, take an element in S. If it is more than 2, then we are going to build this set. So M is a set of all x's in S such that they are more than 2. So this is what we have written in a set builder notation. So the translation of this into Haskell will be like this. Now we change the set to a list. Change the set to a list, and membership function of the set we are writing this way. It is not membership function, it is a list. Because it is a list, we are telling as if x is a member of this list S. S will be now a list. and then we are checking x greater than 2. So what we are doing? We are getting a list obtained from the given list S, and then we are obtaining the same list, same members we are getting as we have done for set, but now we are looking at it as a list. So this representation carries over, and then this is what to do. So what are the components? Let us first do see. First we are generating an element. This x arrow, left arrow, this is generating an element of the set S. Then we are testing whether it satisfies some property. Yes, it is satisfying greater than 2. If that be the case, we are transforming this x. We are transforming this identity. The x greater than 2 is true, then we are going to keep it x. So then our new list will be 3, 4 and 5. So 2 here, 1 and 2 for this, the property is false. So 3, 4, 5 we have got. So another important aspect here, the what to do, why it is what to do, it is because when we are doing in the selecting, when we are checking an element from the set, it is not that we will check the first element of the set or the last element of the set. Which way the element we are going to select, that is not specified. It is also not of our concern. So the choice is purely non-deterministic. So what it says, if I take an element of the set S, it should be greater than 2. If it is greater than 2, I will keep it, otherwise I am going to discard it. Same thing it is done here. So we have written that take an element of this list and then check whether it is greater than 2. How it is going to implement this x, it is not known to the user, and the user need not be bothered about it. This is the what to do, not how to do. Moreover, we instead of this simple function like x transforming into identity, we could have here written it will be 2x or 3x, 3 times x. That means it is now transforming x to 3 times, multiplying it by 3, and we are getting a new elements. Here in this example, elements are same as in the given list, but now we are getting new elements by doing the transformation. So this is the idea of list comprehension. Okay, now we consider list in Haskell. List is a very important data structure in Haskell, and lists are represented in this way. So this is one list, non-empty list. This is an empty list, and this is a list of with one element. So length of an empty list is 0. Now a non-empty list is written as this way as well. We can write it is a head and a tail. So this is the thing we discussed in pair. So this is a head and this is a tail. Now how is a list constructed in Haskell? So 2, 3, 7 we can write it, decompose into head and tail. We go on doing it until we get the empty list. So again 3, 7 we can write it as 3 colon 7. Again 7 we can write as 7 colon this. Now this operator, the constructor is right associated. That means we can put a braces here. So again this is head tail, this is head tail, this is head tail. Within a tail we have embedding of head and tail. How long can we go? We can go until we come to the empty list. So this is the list is. So this is exactly how a list is constructed internally. So first we start with an empty list. So then 7 and empty will be combined to get an 1 element list. Then 3 and 7 will be combined to get this 3, 7. Then finally 2 colon 3, 7 will give us 2, 3, 7. So we have seen how that list is then constructed. So 2, 3, 7 is constructed from the empty list. Then it goes in the reverse direction. So it goes this way. So elements are added to the front. So you have the empty list, then we added one element at the front, then added the other element, second element, then finally the third element. So the constructor has type. We will always associate with any function, we have a type of the function, the input and the output. So it says that the head, there are two things, head and tail. It takes as input a head and a tail. That means if the list is of, when we say list is of type A, that means the list is of type integers. That means it is elements are of type integer. Now this notation says it is a list. This notation says this is an element. So here it is an element of type A in the list. That means we have a list of integers. This means a list of integers means each element is an integer. Each element is a, so head is an integer and this a tail is a list. It is a list type. This notation says list type and output is a list. So this is how we write type signatures in Haskell. Now length is an again, and there are several inbuilt functions in Haskell to do different operations on list. So length, for example, is a very common function. Length of a list will give the number of elements in a list. So let us see how it is internally implemented. So it is taking a list of integers and it will give on the returning an integer. Now length of empty list is 0. And if it is non-empty, so here the idea of style of writing these two things, these arguments will be always empty and non-empty. So Haskell, when it comes processes, it is a top-down processing. If you give an input empty, it will say it is empty and it will stop. If it is non-empty, it can always break it up into head and tail. So it is written as x colon xx. So it is the convention, write x colon xx. Xs is actually you should you can read it as xx. Xx actually we write xx means too much. So we write, so actually we did excess. So we had deleted. So we got xx. So this xx then we are recursively doing 1 plus length of xx. So recursively we are going to evaluate it and we are going to get the length of the list. For example, if I have a length 3 element list, so this should give us 3. So how it will work? It will be 2, 3, 5 will be length of head and the tail. Now 2, 3, 5 this matches here, so I am going to get 1 plus length of 3, 5. Again it will be decomposed into head and tail. 1 plus it will be, this will be 3, 5. There will be 3, 5. So there will be 1 plus length of 5. Then again 5 colon empty. So this will be 1 plus length of empty. Now length of empty is 0. So it stops here and we are getting the length of the list as 3. Now let us see how to write the quick sort algorithm in Haskell. So we are doing quick sort on a list of integers and we are going to get another list of integers, that is input is not sorted say and the output is a sorted list of integers. That means say suppose increasing in an increasing order, says all the elements suppose they are distinct, so our output will be in an increasing order. So it is defined like this. Empty list quick sort it will get, it will be empty. Empty list quick sort we are going to get empty. If the list is empty, we are going to get empty. Empty list will be output. If it is non-empty, then what this says? So this operator is the concatenation operator. So that means this says AX says that there is one element, that is one element list. To the one element list, you are concatenating two other lists. This is the concatenation. So what it is concatenating? This set list comprehension it is doing. That means on the right of this element, we have a list that contains elements. All the elements are more than this x. It says that in this xx, from the original list xx, we have taken those elements that are more than x, and then we are performing quicksort onto them. On the left we have elements, this is the list, this is all the elements are more than greater than x, and there we have less than x. Here we have all the elements less than x, and we are performing quicksort onto them, the recursively quicksorting on the two things. So you see, it is important to appreciate how the idea of quicksort is embedded into this definition here of when the list is non-empty. It is exactly the definition of quicksort. What does x is? X is what is called the pivot. So that means a final thing. What it says, the final output will be a list where x will be placed somewhere. If I place it somewhere, if I look at the right hand side of things, all the elements will be more than that. And if I look at the left hand side of x, it will be less than, equal to that. If they are distinct, then left hand side will be less than right hand side. This is what the idea of quicksort is. Now, if you want to write in a traditional imperative programming language, how are we going to achieve it? We recall that what we did, we had a partitioning auxiliary function. The partitioning function used to do this job. We take the pivot and it used to create subarrays. Left subarray will have all elements less than equal to x, right subarray will have all greater than, and then we recursively apply quicksort. That was the idea. That means the partitioning point we have to tell the Turing machine how to get. Okay, if I tell the Turing machine will rearrange all the elements left, right and all, finally it will bring x to a position such that this constraint is satisfied. That is what we call how to do. See the contrasting difference between these two here. What to do is telling, look, this is my definition of quicksort. I am going to place x somewhere. Where it is I don't know. But wherever I place it, all elements on the right will be more and all elements left will be this. And then I recursively apply quicksort and my job is done. So this is an essence of what to do rather than how to do. So there we don't have any partitioning function. And we have achieved this code in 2 lines, and understanding it is also very neat. Their understanding, we have to understand what is the partitioning. We need to know how actually a partition is done. Here we don't know. So if I already have a good knowledge of quicksort and I want to just implement it, so this algorithm also gives a correct algorithm. The correctness of quicksort relies on the correctness of partition. Here we don't have to do any partition. We say, okay, look, this is the definition of quicksort and I have written it in some way. And if this definition is correct, my program should be correct. And that is the essence of what to do. So it embeds recursion, list concatenation, and list concatenation is available within that. It can be also defined recursively, and we have list comprehension. Now we will study Haskell from the perspective that how the features like lambda abstraction, definitions, they are really translated, carrying, they are actually embedded in Haskell. So we consider a very simple example, like a square is a function that takes an integer and returns an integer. So the body of square is, so square x, we write square x. So we write it in this way. X is the parameter and the body is x multiplied by x. And this is the type signature. First line of Haskell will always be a type signature. It is written name, then 2 colons, and then you write int arrow this. This is maps to. That means the mapping from integer to integer. And here we write a parameter square x, right hand side of equal to is the body of this function. And so in lambda x also we do a body of the function is, instead of dot, we write dot here equal to x dot x square, and here square x. Here this is anonymous, this is not anonymous, this has a name. So we will soon see that it can be translated as anonymous. So here the idea was that Function application, then function, it is just written what is this function is going to do. Lambda x dot x square is what? The abstraction is written. Then we want to add two numbers. So it says that it takes two integers as input and returns another integer. So the body of add will be add xy will be x plus y. So this is same as lambda x dot lambda y x plus y. This is the function abstraction is done this way. Now we want to see how these functions are, when they are applied to arguments, how they work. So we know currying is transforming a function of n arguments into n functions of one argument each. So here this add function, then it says you take an integer, two integer, return integer. Now arrow is right as associative, so we can put an brace here. So what it now says, it takes an integer and returns a function. That takes one integer and returns a function, another integer. So it is this technique that we know is called currying. So add xy is x plus y. So this is our lambda representation here. So now we have to do application, but now we are doing partial application. So when we do add 2, we will get a function int arrow int. So here what we do, when we apply this x is 2, so we get x is replaced by 2, so we get another function lambda y dot y plus 2. So this part is here is allowed in Haskell. That means I have not applied add two parameters. I have given input only one parameter. If I stop here, it is okay, perfectly okay in Haskell. So it is partial application. So add 2 then becomes a new function. So we can call it add 2 or if add prime, whatever. Now add 2 when applied to 3, it gives an integer. So same thing happens here. Lambda y dot 2 plus y 3, we get here 2 plus 5, 2 plus 3. So function application, we know that function application is left associative, but these arrow types, they are right associative. So here add 2, that is why add 2 we have the braces. Is in add, we know that mnp is equivalent to mnp, left associative. Now if we want to do uncurried version, that means I want to use the 2 arguments at a time. That means I will take a pair as input, pair of 2 integers as input, and gives a integer. So uncurried you see x, y, x plus y. This is what we do in a normal imperative programming language, a C language. You cannot supply one argument and then do the another argument. You have to supply both the arguments together. So what we are actually doing, we are actually supplying an uncurried version. That version that we are used to working is called curried version. And Haskell on the other hand, it will always do by currying. Now we want to see how lambda abstraction means that you are working in an anonymous mode. Earlier square function is not anonymous, add is not anonymous. Now we can rewrite them and make it anonymous. So the way of doing it is, so we have lambda x dot this. So this dot corresponds to this arrow. Lambda corresponds to this backslash. This parameter x we write beside this backslash. So backslash x arrow means lambda x dot. Then whatever you write becomes the body. So this is the translation of a lambda expression, that is the abstraction in Haskell. So if we have a single argument, so lambda x dot x plus 1 we write as backslash x arrow x plus 1. Now when a function is applied, we do beta reduction here and get 5 here. So here lambda x arrow x plus 1 4, this will output will give us 5. Now when we do multiple arguments, so a compact way of writing in lambda calculus is lambda x dot xy dot x plus. We don't write lambda, so many lambdas we don't write. We can compact it in this way. The shorthand of writing multiple arguments. Same thing we do here. Instead of lambda, you write backslash xy, written xy, dot is written dot, and you write xy. This is the same as lambda x arrow. Then this part is again a function. because this one is lambda x dot lambda y dot x plus y. So after lambda x we have another function. So this is this part. So actually this part then means lambda x arrow within bracket lambda y arrow x plus y. So this is the Haskell. Haskell carries function by default. So that means it will consume one argument at a time. It is exactly in the curried manner it is going to work. Taking an argument, partial application, creates another function, goes on to it, and we are attaining the final result. Now recall that we had a term like self-application, that means it led us to non-terminations. So lambda x dot xx. So say we can write this SA in Haskell is written as omega is equal to lambda x arrow xx. Again it is a function. And then this is applied to SA, so this will be lambda x dot xx. Evaluating this will cause non-termination infinite loops. So you have to stop it. If you want to run this code, you have to stop it. Deliberately you have to terminate this code. Next is function composition. Function composition we write denoting this way. So f dot gx means f gx means apply g to x first. Then the result, onto the result you apply f. So that means what in lambda it will be lambda f lambda g. There are two functions that it takes as input. First it applies to g and then it applies to f. So then the type will be if x has type A, then g will be of type A arrow B. That means return type of g is B and f type will be B arrow C. So the overall type will be return type is C. So it will be B arrow C within braces arrow A arrow B. This means this is a function type, this is a function type, this is a variable type, and these are functions, and this is a variable. So we write in lambda is lambda here this one will return as lambda fgx arrow fgx. So it is a straight away translation of anonymous way. The lambda notation is straight away translated to Haskell in this way. So we are writing anonymous mode. That means we can write, basically we are writing lambda programs in Haskell. So for example, if we have f is equal to multiply by 2, doubles a number, and we add a number, so we write plus 3. So h is FOG, f composition G. Hx is defined as f of g of x is equal to x plus 3 star 2. So we replace it by star 2, then here plus 3 4. So that means we are adding 3 to 4, so we are getting 7 multiplied by 2 4. So here also if you have done the same thing, 4 plus 3 7, you got function composition. Now a higher order function. So in higher order function, so function composition is again higher order function. You are taking higher functions as input, and it may take either it will take a function as input or return a function or both. So here one very important thing, as we have seen in the first example, when we are doing sum of m square of sigma j square j is equal to 1 to n. So here we have seen map function. Map is a very important function in Haskell and it is a higher order function because it takes one function as input and a list. It takes one function, a list as input, return. That means what? So if I have a list of some elements and a function is there and x is an element, this list will be transformed to f of this, f of this, f of x, f of this. This transformation is what we want. That means all the elements of the list will be transformed into something. That is, we are applying a function called map. So one is this function, another is a list of elements of type A, whatever might be. So the A type A. So for example, we have a list of integers and output will be a list of integers. We want to square it. every element will be square. That example that is in j square, sigma summation j square, j is equal to 1 to n. So here it is written in anosymous mode as lambda x maps to x square, 1, 2, 3 as input. So that means each element will be transformed to x square. So 1 will map to 1 square, 2 will map to 2 square, 3 will map to. This is what happened in that example. So map created, transformed this list input list to this one. So then internally let us see how this will be defined. So if I apply f is now general, anything. This was an instance. This was an instance of map. So a general structure of map is, if I apply f to empty, it will be empty. If I apply onto a non-empty list, I will apply f to x, and this is the constructor, and the tail will be map of recursively f of xx, and that's it. So this is the map function. So the structure you see of recursion is same in all the examples that you see. The structure of recursion is more or less same. Well, however, this is a higher order function. Now there is another function, that is a filter function. Now earlier what happened was, if I take a list of length n, the output will also be a list of L prime will also be of list n. Now suppose I want to filter, means this list of list n, I want to reduce it to n prime where n prime is less than n or less than equal to say n. So that means I am filtering, that keeping only things that are there and other things I am discarding. So then the output is, the function type is AR of bool. It will test an element, see the truth of the element, true and false. If it is true, it will keep it, false, it will discard it. So there are two inputs, one is a list, another is a function, and returns another. It is like map, but it is a little bit different. For example, if I have a list is 2, 3, 6 and I want to keep those elements that are divisible by 2, that means they are even. So if a number is even, I am going to keep it, if not even, I want to discard. So filter is even 2, 3, 6 will give us 2, 6. So is even, we can say that when n divided by 2, the remainder is 0. That is a modulo operator, we do like this. So so this is again an instance of filter. So in general, filter p x colon xx will be, now you have a guards here. Now you see the usage of guards. So then what we are saying, if x satisfies some property p, then we are going to keep it, otherwise we are going to discard it. So we write px means x, the property p holds for, that means here x is even or not. If x is even, we are going to keep it and continue with the tail of the list. Otherwise, we are going to discard it and continue with the tail of the list. So that's the idea of filter. It is again a higher order function. Now in Haskell, another important feature that we have seen is lazy evaluation. So recall when we studied lambda calculus, we said normalization, that means given a term, we want to reduce it to a normal form. This normal form. So there are different ways of doing it. One that we studied is called call by name. That call by name idea is that meaning is that lazy evaluation. So Haskell employs this idea of call by name, but it actually is a more optimized version, which is called call by need. So that means in call by name, each argument will be reevaluated every time. So we do a memoization and we use it only once, and that means we are caching it in some way, and then we are using that technique, which is nothing but an optimization. It is a call by name. So the idea here is, so if I am doing call by name for normalizing, if I have a term like lambda x dot yn, so that means x does not occur in the body of the function. So then there is no need to evaluate n. So answer is y, beta reduces to y. That means the idea about call by name is evaluate the argument only when it is needed. That means when the need arises, we will evaluate n. Otherwise, we are not going to evaluate n. That means the n, whatever it might be, n could have been a very huge lambda term. We know the answer is always y, so we will not touch n at all. This paradigm is used in Haskell. So here, for example, in this example, fxy is x plus y. Let x is 9 minus 3 and y is this f of these two numbers. Now, one way I will evaluate this argument, x will be then 6 and then f will be this, but I will not touch it unless it is required. So, when I am using fxy, I am supplying x as it is. So, here x is 9 minus 3, call by name will place it as it is, and this will be f of 34 3. So, this one is then replaced as x plus y. So, this is x, this is y. This is now simplified and we get 6 here. Now again f of x plus y sort of a thing, you are again getting x plus y. So we get 43. Now suppose instead of x plus y we change y to 5. Now if we apply f of 34 3, what will happen? 34 3 here when it comes, that means it f of this whole thing, f of 9 minus 3 and f of this x is the 9 minus 3, but x is not, y is not occurring here. So this corresponds to y, this corresponds to y. This is not occurring here, so y will not be evaluated. Now this part will not be evaluated at all. So it will be x plus y, then 9 minus 3 will be evaluated 6 and 6 plus 5 we are going to get 11, and that's the idea. So this is lazy evaluation in Haskell. So this is in accordance with the call by name semantics that we studied in lambda calculus. So we can summarize what we have discussed. We have discussed different features of Haskell and we have seen how lambda concepts like abstraction, currying, function applications, lazy evaluation, order functions, they are all translated to in Haskell. So the book that we followed for this, some examples we have taken. So it is from this book by Simon Thompson, The Craft of Functional Programming, and this book is available online. So you can take a look at this book, very nice book. And you can also write programs online via haskell.org. So at the command prompt you can write simple programs and you can see how it is working. So we stop here. Thank you for your kind attention.